Think about this for a second. Space has always been there. Every single night of every single year of every single century of human existence, people looked up and saw it. Stars, planets, the moon hanging in the dark. And yet, for most of history, nobody actually knew what they were looking at. They could see it, they just couldn't understand it. So when we ask the question, who discovered space? The answer isn't one person, and it isn't one moment. It's a chain of human beings spread across thousands of years, each one adding a piece to a puzzle so massive that we're still putting it together today. And the story of how we went from ancient people staring at the sky and making up myths to sending metal machines to the edge of the solar system is one of the most unbelievable stories in the history of our species. So let's go all the way back to the beginning, because that's where this story actually starts. The earliest civilizations on Earth were not primitive in the way we sometimes imagine. The Babylonians, living in what is now Iraq, were keeping detailed written records of the sky as far back as 1800 BCE. They tracked the movements of the moon, the sun, and 5 visible planets with a consistency and precision that genuinely surprises modern astronomers when they study those ancient clay tablets. They weren't doing this for fun. They were doing it because they believed the sky was the language of the gods, and if you could read it, you could understand fate. That belief, superstitious as it sounds, forced them to become the world's first real astronomers. They built calendars. They predicted lunar eclipses centuries before they happened. They recorded the periodic return of what we now know as Halley's Comet. They weren't thinking about space as a physical place. To them, the sky was a spiritual ceiling, but in trying to read it, they accidentally became the first people to study it systematically. The ancient Egyptians were doing similar things around the same time. The pyramids at Giza were aligned with extraordinary precision to specific stars. The Great Pyramid is aligned almost perfectly to true north, and the shafts inside the structure appear to have been oriented towards certain stars that held religious significance. The Egyptians used the position of the star Sirius to predict the annual flooding of the Nile, which was the heartbeat of their entire civilization. Again, spiritual motivation producing scientific observation. The sky was being watched with incredible intensity, even if no one understood yet what they were watching. But the Greeks are the ones who started asking a different kind of question. Not just what does the sky do, but what is the sky actually made of, and how does it work? This shift happened gradually, over several centuries, and it changed everything. Around 600 BCE, a thinker named Thales proposed something revolutionary for his time, that the universe could be understood through reason and observation, rather than through mythology. He was wrong about most of his specific ideas, but the intellectual posture he adopted, that nature follows rules that the human mind can figure out, set the stage for everything that followed. Then came Pythagoras, who believed that the Earth was a sphere, not flat, not a disk floating on water, a sphere. This was around 570 BCE, and the reasoning he used was based on observation. He noticed that the shadow the Earth cast on the moon during lunar eclipses was always circular, regardless of the angle, and a shape that always casts a circular shadow from multiple angles has to be a sphere. This sounds simple now, but 2,500 years ago, in a world with no satellites and no photographs from orbit, this was a stunning intellectual leap. He was right, and it's worth pausing on that. Someone figured out the Earth is round more than 2,000 years before the first airplane flew. Then around 270 BCE, a Greek astronomer named Aristarchus of Samos proposed something even more radical. He argued that the Earth moves around the sun, not the other way around. He called this the heliocentric model, and he supported it with actual geometric reasoning. He tried to calculate the relative sizes and distances of the Earth, moon, and sun using the angles during lunar eclipses. His numbers were off. The tools of his era couldn't give him precision, but his idea was correct. The Earth orbits the sun. He had it right. And for about 1,800 years, almost nobody listened to him. The reason was Ptolemy. Claudius Ptolemy was an Egyptian mathematician and astronomer working in Alexandria around 150 CE, and he constructed one of the most detailed, mathematically sophisticated models of the universe ever produced in the ancient world. His model placed the Earth at the center of everything, with the sun, moon, planets, and stars all moving around it in complex, circular paths. He called his work the Almagest, and it was so well organized, so mathematically persuasive, and so consistent with the everyday experience of watching the sky that it became the dominant model of the cosmos for nearly a millennium and a half. Ptolemy was wrong about the big picture, but right about enough of the details that no one could easily dismiss him. His system could actually predict where planets would be in the sky with reasonable accuracy, which gave it enormous staying power. And the Catholic Church later adopted his Earth-centered model because it aligned neatly with a theological worldview that placed humanity at the center of creation. That combination, scientific plausibility plus religious authority, made the geocentric model nearly impossible to challenge for over 1,000 years, until Nicolaus Copernicus decided to challenge it anyway. Copernicus was a Polish mathematician and cleric born in 1473. And he spent decades quietly working on a model of the universe that placed the sun, not the earth, at the center. He wasn't the first to think this. Aristarchus beat him by nearly 2,000 years. But Copernicus built a complete, mathematically coherent system that could stand up to scrutiny. He called it the heliocentric theory, and he was so nervous about the reaction it would receive that he delayed publishing his major work, a book called On the Revolutions of the Celestial Spheres, until the very end of his life. The story goes that he received the first printed copy of the book on the day he died in 1543. Whether that's precisely true or slightly embellished, the symbolism is fitting. He detonated a conceptual bomb and stepped out of the room before it went off, because the explosion was coming. The Copernican model didn't immediately overturn the established worldview, but it created a crack, and a man named Galileo Galilei walked straight through it. Galileo was an Italian astronomer and physicist, born in 1564, and he is one of the most consequential figures in the entire history of science. In 1609, he heard about a new invention coming out of the Netherlands, a device that used lenses to make distant objects appear closer. We call it the telescope. Galileo didn't invent the telescope, but he improved it dramatically, building instruments that were far more powerful than anything that existed at the time. And then he did something that no one had thought to do. He pointed one at the sky. What he saw broke the geocentric model beyond repair. He observed the moon and saw that it wasn't a perfect smooth sphere. It had mountains, valleys, and craters. This was a problem for the old cosmological view, which held that everything in the heavens was perfect and unchanging. Then he looked at Jupiter and discovered 4 moons orbiting it. Moons, orbiting another planet. Not everything moved around the Earth. That single observation was devastating to Ptolemy's framework. He observed the phases of Venus, the way Venus appeared to go through cycles of illumination, much like the moon does, and that could only be explained if Venus was orbiting the sun. He observed sunspots on the surface of the sun, another blow to the idea of heavenly perfection. He observed that the Milky Way was not a smear of light, but was in fact composed of vast numbers of individual stars, far more than the naked eye could resolve. Galileo published his observations and supported the Copernican model openly. The Catholic Church eventually had enough. He was tried by the Inquisition in 1633 and forced to recant his support for heliocentrism. He spent the rest of his life under house arrest. But the knowledge couldn't be put back. The observations were already out there. Other scientists had already read his work. The universe had already been revealed to be something completely different from what the Church was teaching. While Galileo was making his telescopic discoveries, a German mathematician named Johannes Kepler was working out the precise mathematics of how planets actually move. Kepler had access to incredibly detailed observational data collected by a Danish astronomer named Tycho Brahe, who had spent decades recording planetary positions with astonishing accuracy, long before telescopes existed. Using that data, Kepler worked out 3 laws of planetary motion that transformed astronomy forever. The first said that planets orbit the sun not in perfect circles but in ellipses, slightly elongated ovals, with the sun at one of the focal points. The second described how planets move faster when closer to the sun and slower when farther away. The third related the time it takes a planet to complete one orbit to its distance from the sun. Kepler published these between 1605 and 1619, and they were mathematically exact. They matched the observational data perfectly. There was no longer any reasonable scientific argument against the heliocentric model. The solar system was not Earth-centered, it was sun-centered, and the planets, including Earth, were moving through space according to precise mathematical laws. The next giant step came from a young English mathematician who, according to legend, sat under an apple tree and watched a piece of fruit fall to the ground. The legend is probably a simplification, but the insight it represents was entirely real. Isaac Newton, born in 1643, worked out the law of universal gravitation, The idea that every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. Gravity wasn't just something that made things fall on Earth. Gravity was the force that kept the moon in orbit around the Earth, that kept the Earth in orbit around the Sun, that organized the entire structure of the solar system. Newton published his landmark work, Principia Mathematica, in 1687, and it didn't just explain the solar system, it gave humanity a set of mathematical tools powerful enough to calculate the movements of every object in the universe. Kepler had described what the planets did. Newton explained why. By this point, humanity understood that the Earth was one of several planets orbiting a star we called the Sun, and that this system was held together by gravity, and that it operated according to mathematical laws that could be calculated with precision. But the universe was still thought of as relatively small. The stars were thought to be fixed points on a kind of ceiling, not terribly far away. That idea would also be shattered, in time, as astronomers began to measure stellar distances and realized that even the nearest star to our Sun is so far away that light, moving at 300,000 kilometers per second, takes more than 4 years to travel from there to here. And the universe stretched out beyond that in every direction, across distances so enormous they strain human comprehension. But understanding what space is and actually going there are two very different things, and the story of how we got from one to the other is its own incredible chapter. For most of history, even the most visionary scientists assumed that space was permanently out of human reach. There was simply no conceivable way to get off the planet. And then, in the late 19th and early 20th centuries, almost simultaneously, a handful of thinkers in different countries started working on an idea that would change the world: the rocket. The first person to do serious scientific work on the mathematics of space travel was a Russian schoolteacher named Konstantin Tsiolkovsky. Born in 1857, Tsiolkovsky was largely self-taught, partially deaf from childhood illness, and spent most of his life in obscurity in a small Russian town. But in 1903, the same year the Wright brothers made their first flight at Kitty Hawk, he published a paper that laid out the fundamental mathematics of rocket propulsion. He derived what is now called the Tsiolkovsky rocket equation, which describes exactly how a rocket accelerates as it burns fuel and loses mass. He understood that liquid fuel would be necessary for space travel, that rockets would need to operate in a vacuum, that multi-stage rockets would be required to reach orbit. He proposed the idea of space stations. He wrote about spacesuits and airlocks. He thought through the colonization of other planets. He did all of this while living modestly in Russia, largely ignored during his lifetime, writing science fiction stories on the side to explore ideas that no one around him took seriously. He is now considered the father of theoretical astronautics. Across the Atlantic, an American engineer named Robert Goddard was taking the next step, actually building the things. Goddard was a physicist from Massachusetts who became obsessed with rocketry, and he spent years working on practical liquid-fueled rocket designs. On March 16, 1926, in a snowy field in Auburn, Massachusetts, he launched the world's first liquid-fueled rocket. It flew for 2.5 seconds and traveled about 56 meters, barely the length of 2 school buses. But it flew, and liquid-fueled rocketry, as Goddard understood, was the only technology capable of eventually reaching space. He continued working throughout the 1920s and 1930s, developing gyroscopic stabilization systems, guidance mechanisms, parachute recovery systems, all the building blocks of modern rockets. The scientific establishment largely ridiculed him. The New York Times published an editorial in 1920 mocking his ideas about rockets operating in a vacuum, claiming he lacked basic knowledge of physics. The Times later retracted that editorial, the day after Apollo 11 launched toward the moon in 1969. In Europe, a Romanian-German physicist named Hermann Oberth was working independently on similar problems. He published a book in 1923 called The Rocket into Interplanetary Space, which laid out the mathematics of space travel in rigorous detail and discussed the practical engineering challenges involved. Oberth's work inspired a generation of German rocket enthusiasts, including a young aristocrat named Wernher von Braun, who would go on to become one of the most influential rocket engineers in history. Von Braun and his colleagues in Germany developed their rocketry under the Nazi regime during World War II, producing the V-2 ballistic missile, the first man-made object to reach the boundary of space. The V-2 crossed the Kármán line, the internationally recognized boundary at 100 kilometers above sea level that separates Earth's atmosphere from outer space, during test flights in 1944. It was a weapon of terror that killed thousands of civilians across Europe, but the engineering that made it work was real, and it became the foundational technology of both the American and Soviet space programs after the war. Von Braun himself was brought to the United States under a classified government program and eventually led the team that built the Saturn V rocket, which carried the Apollo astronauts to the moon. And the Soviets, using captured German rocket technology and their own formidable engineering talent, launched the space age. On October 4, 1957, the Soviet Union launched a small metal sphere about 58 centimeters in diameter, weighing roughly 84 kilograms, into orbit around the Earth. It was called Sputnik 1, and it changed the world overnight. Sputnik transmitted a simple radio beep as it orbited, and anyone with the right equipment could pick it up. Amateur radio operators across the United States listened to it in real time, tracking the Soviet machine as it passed overhead every 96 minutes. The psychological impact in America was immense. The United States had assumed it was ahead in science and technology. Sputnik proved otherwise, and for the first time in human history, something built by human hands was in orbit around the Earth. Space had been entered. The Soviets followed up Sputnik 1 with Sputnik 2, which carried a dog named Laika into orbit in November 1957. Laika became the first living creature to orbit the Earth. She did not survive the mission. The technology to bring her back safely didn't exist yet, and this was known before launch. The ethics of that decision have been debated ever since. But the mission proved that a living organism could survive the conditions of launch and microgravity, at least in the short term, which was crucial information for human spaceflight planning. The United States scrambled to respond. The American space program was initially fractured and poorly coordinated, and the first few attempts to launch satellites ended in embarrassing failures on live television. Then, in 1958, NASA was created, the National Aeronautics and Space Administration, to consolidate America's civilian space efforts, and the space race was officially on. But the Soviets got there first, again. On April 12, 1961, a 27-year-old Soviet Air Force pilot named Yuri Gagarin climbed into a small spherical capsule called Vostok 1 and became the first human being in space. His mission lasted 108 minutes. He completed one orbit of the Earth. He reached a maximum altitude of about 327 kilometers. He experienced weightlessness for the first time in human history, at least the first time any human had experienced it in actual space, rather than in a simulated environment. When his capsule re-entered the atmosphere, it was not designed to land gently, so Gagarin ejected at high altitude and parachuted to the ground separately from the capsule, landing in a field in Russia, where a woman and her granddaughter reportedly watched him descend in his orange flight suit. He became one of the most famous human beings on the planet overnight. April 12 is still celebrated as Cosmonautics Day in Russia. America answered 23 days later. On May 5, 1961, Alan Shepard became the first American in space, riding a Redstone rocket in a capsule called Freedom 7. His mission lasted 15 minutes and 22 seconds, a brief suborbital arc compared to Gagarin's full orbit. But it was enough. It proved the American program was functional. And then, 20 days after Shepard's flight, President John F. Kennedy stood before Congress and delivered one of the most audacious public commitments in political history. He declared that the United States would land a man on the moon and return him safely to the Earth before the end of the decade. What followed was one of the most extraordinary engineering efforts in human history. At its peak, the Apollo program employed around 400,000 people. It consumed roughly 4% of the entire federal budget. It required the development of entirely new materials, new manufacturing processes, new computer systems, new navigation techniques. Astronauts flew increasingly complex missions, first orbiting Earth, then orbiting the Moon, then attempting a landing. There were tragedies along the way. In January 1967, a fire broke out during a ground test of the Apollo 1 capsule and killed all 3 crew members, Gus Grissom, Ed White, and Roger Chaffee. The program was grounded for 20 months while engineers redesigned the capsule from the ground up. And then, on July 20, 1969, Apollo 11 landed on the surface of the Moon. Neil Armstrong climbed down the ladder of the lunar module, stepped onto the lunar surface, and said words that have been heard billions of times since. A human being was standing on another world for the first time in the history of our species. Buzz Aldrin joined him minutes later. They spent about 2.5 hours on the surface, collected rock and soil samples, planted an American flag, and left behind a plaque that read, in part, We came in peace for all mankind. Michael Collins orbited above them in the command module, alone, further from any other human being than anyone in history had ever been. 5 more Apollo missions successfully landed on the moon after that, the last being Apollo 17 in December 1972. A total of 12 human beings have walked on the surface of another world. All of them were Americans. All of them went in the span of about 3.5 years. And then the Apollo program was canceled, and no one has been back since. But the exploration of space didn't stop. It shifted. Robotic spacecraft began going where humans couldn't follow, at least not yet. In 1973 and 1974, the Pioneer 10 and Pioneer 11 spacecraft became the first human-made objects to travel through the asteroid belt and reach Jupiter. They carried gold plaques on their sides bearing a diagram of a man and a woman, a map showing Earth's location relative to several pulsars, and other information that could theoretically allow an intelligent extraterrestrial civilization to identify where they came from. In 1977, NASA launched Voyager 1 and Voyager 2, 2 spacecraft that would conduct detailed flybys of Jupiter, Saturn, Uranus, and Neptune. Voyager 1 is now the farthest human-made object from Earth, having crossed into interstellar space, beyond the boundary of our Sun's influence, in 2012, more than 45 years after it launched. It is still transmitting signals back to Earth. Those signals, traveling at the speed of light, take more than 22 hours to reach us. Humanity also built eyes in orbit. The Hubble Space Telescope, launched in 1990, has provided some of the most profound and beautiful images of the universe ever captured. Deep field images showing thousands of galaxies in a patch of sky that appears blank to the naked eye. Each galaxy containing hundreds of billions of stars, each potentially surrounded by planets, some potentially capable of supporting life. When you look at a Hubble Deep Field image, you are looking across billions of light years of space, seeing galaxies as they existed billions of years in the past. You are looking backward in time. The International Space Station, assembled in orbit beginning in 1998, has been continuously inhabited since November 2000. Human beings have lived in space without interruption for more than 2 decades, conducting experiments in biology, physics, medicine, and materials science that can only be done in the microgravity environment of orbit. Over 270 people from more than 20 countries have visited it. And now, in the 2020s, the conversation about space has expanded in ways that would have seemed like science fiction just decades ago. Private companies like SpaceX, Blue Origin, and others have built operational rockets and spacecraft. SpaceX has flown paying civilian passengers to orbit. NASA's Artemis program is working to return humans to the moon, with plans that include landing the first woman and the first person of color on the lunar surface. There are serious, funded, detailed engineering plans for eventual human missions to Mars. The James Webb Space Telescope, launched in December 2021, has pushed our observational reach further than ever before, capturing images of some of the earliest galaxies to form after the Big Bang, looking back to within a few 100 million years of the beginning of the universe itself. So who discovered space? The honest answer is that it was everyone. It was the Babylonians watching the sky on clay tablets 3,000 years ago. It was Aristarchus reasoning about orbits on the island of Samos. It was Copernicus quietly rewriting the cosmos while the church wasn't looking. It was Galileo pointing a telescope upward and seeing moons around Jupiter. It was Kepler doing mathematics so precise that they still hold today. It was Newton connecting falling apples to orbiting moons. It was Tsiolkovsky writing rocket equations in a small Russian town while nobody paid attention. It was Goddard launching a liquid-fueled rocket from a snowy Massachusetts field. It was the engineers who built Sputnik and the people who launched it. It was Yuri Gagarin, strapped into a capsule on top of a rocket, trusting everything to the work of thousands of people he would never meet. It was Neil Armstrong taking one small step. It was the 400,000 workers who made that step possible. Space was not discovered by a single genius in a single moment. It was revealed, piece by piece, over thousands of years by human beings who refused to accept that the darkness above them was unknowable. Every answer they found opened 10 new questions, and we are still out here, still asking them, still looking up, still trying to understand what we're actually looking at. That drive, that refusal to stop asking, might be the most genuinely human thing about us. And it has taken us from drawing constellations in the dirt to sending machines beyond the edge of the solar system. Wherever this goes next, the story is still being written.